get looking at section 2.2. Okay, 2.2 and 2.3 become one combo assignment, so you're turning in both at the same time. All right, so we're kind of in the middle of limits now. We're kind of right in the thick of things, and I'm going to do something with you. We're actually going to do one of the problems in your assignments. Now, you can do kind of what you want with this. I mean, you're definitely, I would suggest that you watch. You certainly can write it down, but I'm just telling you, I'm actually doing one of the problems in your assignment. Now, will you redo it for your assignment? Yeah, you'll redo it. I guess it's up to you how you redo it. You could look at what you're going to write down, or I would recommend that you would kind of feel like you're doing it for the first time again. But there's a reason I'm going over this problem on page 72, because usually students have questions on it. And you find out, if we just talk about a little bit, that most students say, all right, that's all I had to do. Okay, so remember, a lot of times in your assignment, you're going to see things that require you to make connections from the lesson. And I guess what I'm going to do right now is kind of help you make that connection so there's a little smoother transition with this problem. Look at it. Don't just wait for me. Like right now, look at number 49. Read the directions above it and just kind of get an idea why we're going to end up talking about this. Okay, now, do you realize what sort of the objective is? We're trying to draw something. The thing that the first time you do one of these, the kids often ask, so how many drawings am I creating? Well, the answer is 1, but it's going to have all of this stuff. Okay, so I want to try to help you to make this connection. Okay, so we got these limit statements. Now, the first one, you don't necessarily have to write it down, but the first one does say the limit as x approaches 1 is equal to 2. Now, what you need to be able to do with a statement like that, like I was trying to get you to do yesterday with the chart activity. By the way, nice job with the chart activity. I always like giving you some bonus points. I more like seeing you guys figure this stuff out. So this actually would have been in your first category. I remember Bryce was writing some stuff down. This is kind of like a good old limit, you know, back when it was just the intended height. So we have a graph that has an intended height of 2 at x equals 1. How do you sketch that? Okay, I don't think you'll be too surprised when I show you that you're simply going to have a y value of 2 when you're getting close to an x value of 1. And I'm just kind of putting these little squiggles beside this because you need to start to create a graph. Okay, so those little squiggles are kind of saying, okay, there's going to be some kind of graph that's around that limit. Now, if you're already saying, why'd you make it a hole? How do you know it's a hole? I don't know. Okay, hold that thought. I don't know if it's a hole. Who knows? Maybe there'll be something that makes me fill that in. Okay, and by the way, if I don't end up filling it in, it's still right. Okay, so I'm just kind of keeping that as a thought. Another pair of limit statements. They're in your book, but sometimes, you know, you see them up here also. Again, something honestly off of your chart, which you guys eventually got in the correct column. As x approaches 5, or from the left or the right, the limit is infinity. Okay, that's always a vertical asymptote. That's always a vertical asymptote. Now, right now, as far as this graph goes, I could mark 5 and I could put a vertical asymptote there because it's going to be true. But as you dig a little deeper into what the book gave you, we have like a left and right limit. So what we can do is be specific. Since it says that it's going to infinity, we have to imply that that's positive infinity. I kind of wish they would have put a positive on the infinity, but since it is infinity, it's positive, so it goes up. It goes up on the left. So now I can start to kind of connect the dots a little bit more. From the left, I can make it go up. See, we can say the same thing on the right. It goes up. Now, again, you have to get a graph. So I need something that I can draw. And again, my little squiggle is to kind of denote that I don't know exactly what the shape is, but I know that there's an asymptote and it goes up on both sides. Do you have any questions so far? Are you starting to get a feel for how you do a problem like 49? Okay, definitely something you will see repeated on a test, even on a quiz and a test. Because what this does, it shows that you can interpret these limit statements. Okay, so I guess the next one I'm picking out here is the one where it says x approaches infinity is equal to -1. Okay, again, something off your chart. Sometimes kids say, should I memorize that chart? You need to understand that chart. You need to be able to interpret it. I don't know if I would memorize, but you should interpret that if x is going to infinity and our value is -1, that means I'm getting closer and closer to a horizontal asymptote. And again, there's a horizontal asymptote at -1 since I'm going out to infinity and getting closer to that value. Again, the reason I'm going over this is to help you guys realize that you just need to connect the dots. So I connected the dot, and we have a little snake. Looks like it's hanging out of a tree, but it's getting closer to that horizontal asymptote. Maybe you feel like you can draw this. I'm moving on to the next limit. It's okay to look back at the chart. That's why we made it. But you want to start to be able to say, okay, this is always a vertical asymptote. We even have some descriptions about positive and negative infinity from the right and from the left. So the little plus sign to the right, the negative infinity says it's going to go down, and then the little negative sign is from the left, and the positive infinity says it's going to go up. By the way I'm kind of sketching this would be completely suitable for an assignment where you guys could do the same thing. I mean, it doesn't have to be like to scale. It doesn't have to be on graph paper. It just needs to show the important features, Is there anything that's going on here that you're wondering, why did you draw it like that? Okay, because there's, I think, 2 more statements. I mean, the author just kind of went berserk here. So we have another limit statement, which is another horizontal asymptote. So again, x goes to -infinity, means that we're going over here to the left side to get a horizontal asymptote. Horizontal and vertical asymptotes are usually denoted with dashed lines. So dashing the lines is good protocol. Oh, I guess that was the last statement. Okay, so you have all those statements. Notice that I kind of pieced it together into one function. It's one function, even though it's all broken up with different features. And by the way, this hole that's in the graph, there's nothing that said that it had to be a hole. What that means is that I could have filled it in. Just again, to be clear, it doesn't matter as long as the limit exists. In other words, as long as the left and the right, as long as you arrive at the diner, okay, then it's correct. Remember the little diner metaphor? I have one more of those videos that I'll show you. I always get a kick out of that guy. What we're going to do today, as we get into this next section, is that we're going to figure out how limits can be used to describe what's called a discontinuity. How can limits be used to describe a discontinuity? So we're not going to learn like a new limit. Okay, the truth is we've learned the limits. You made the chart, but we're going to figure out how limits can describe a discontinuity. And a discontinuity, of course, is a place where you have some type of breakage in your graph. Now, here's kind of the deal. Let me flip to this and let me show you this, and we'll get you a second to get your thoughts together. We've got this graph. It's full of discontinuities. And by the way, probably going to want to sketch it, and I'll give you some time to do that. But we got this graph. It's got some discontinuities. What I'm going to challenge you to do is to try to use limit notation. Okay, that means you're going to write statements on those Post-it notes. So you're going to write limit statements and try to describe what's happening at each of these x values. Now, I'll kind of just give you a little bit of a hint here. You don't have to worry about figuring out something new. I know I use the word discontinuity, but you don't have to like figure out, okay, so what do I do with that? You just need to write some limit statements for each of these x values. And then what I'm going to show you is how those statements you write help us understand discontinuities. Okay, so take a look at the graph. Like I said, most people like to get a copy of it in your notes. On the Post-it notes, try to describe what's happening at each of those x values using limit notation. And then maybe you've guessed that the reason they're on Post-it notes is because I want you to post them up here. Okay, you can bring them up when you're all done. You can bring them up as you go. But again, you can just post them underneath each one of these x values. Make sure you get this little point sort of disjointed down here. Make sure you get that point. So yeah, the idea was use your marker because we're going to want to see them up here. It's hard to see if they're just in pencil. So yeah, when you use your Post-it note, make it big and bold and use your marker. All right, so we have this graph. It's got all kinds of goofy stuff going on at each of these x values, and then we went over and wrote them. Now at x equals -3, we can see that the limit from the left and the limit from the right are both equal to 0, which means that the overall limit is also equal to 0. However, the value at -3 is not the same as the limit. It's a different y value. And so when you have the limit, which is 0, being different than the value, which is -4, we would say that there is a point discontinuity. There is a hole in the graph. By the way, the limit does exist here. We'll talk about that a little bit later in the next video. Now at x equals 0, we have a limit from the left equaling 2, but a limit from the right equaling 3. Now here we see that the left and right hand limits are different, which does mean that the overall limit does not exist. But as far as discontinuities go, this would insinuate that there is a jump in the graph. And again, there's a jump in the graph because the left-hand limit is different than the right. The y values, you have to jump between those y values. At x equals 2, we have a familiar occurrence. It's obviously a vertical asymptote. And we can denote that by saying that the limit is equal to infinity. Now, when the limit is equal to infinity, that also implies a discontinuity. The discontinuity would be an infinite discontinuity. Each one of these limit statements describes a discontinuity. A point discontinuity, a jump discontinuity, and a infinite discontinuity. We'll talk more about each of those in the next video, but I want you to take a look at x equals 4 because it does not describe a discontinuity. You should notice that the limit is 2, but the value is also 2. And when the limit is the same as the value, there's not going to be any kind of break or discontinuity in the graph. Simply put, it's going to be filled in as it normally is. So again, that is not a discontinuity at x equals 4. Now, the horizontal asymptote, you might notice, was not part of this post-it note discussion. That's because horizontal asymptotes are y values, and discontinuities only occur at x values. Another way to put it is that you don't have to pick up your pencil as you approach that horizontal asymptote. So again, horizontal asymptotes are not discontinuities, mainly because they are not x values.